Wild Health is about optimizing you. We use genomics, blood work, biometrics, microbiome assessment, many other tests, and a conversation with you to come up with a full health optimization plan. What's the perfect diet, exercise, and supplement plan for you and only you? The Wild Health podcast is about optimizing all of us. Here we cover the cutting-edge science that gives you the base to be able to apply the personalized plan we give you as a patient. To sign up as a patient, go to wildhealth.com. Or if you're a physician or health coach and you want to learn how to do this for your patients, we're happy to help as well. wildhealth.com for all the information on becoming a patient or working with us.
All right, Dr. Greg, thanks so much for being on the podcast today. We're excited to have you here.
Oh, I'm thrilled to be here as well. Thanks for having me.
Yep, I'm excited to talk about senescence and senolytics. This is an area that I just find super fascinating, and I know one that you obviously know quite a bit about and what we want to pick your brain about today. Maybe we could start just like with the basics, just in case there are any listeners. I think most of them have probably heard of cellular senescence, but let's start with the basics, make sure everybody's up to speed. What exactly is cellular senescence, and why do we even care about it?
Yeah, so cellular senescence really is the idea that some cells have executed a program, so to speak, that won't allow them to make new copies of themselves. So typically what happens is, cells in our tissue will live their fruitful lives, they'll get old, they'll die off, and they'll have replaced themselves with daughter cells, clones, so to speak. Or stem cells will replace cells so that our tissues stay, full and stocked. What happens with a senescent cell is that some degree of cellular stress has been so profound that it's no longer repairable. And because of that, there's almost a brake put on. So don't make copies of yourself. You're too stressed, too damaged. And then what should happen with a senescent cell is that it goes through a cellular process called apoptosis, which comes from a Greek word that translates something like the idea of a leaf or fruit falling off a plant. And so when you think of these, cells being born, living in our tissues, eventually dying, they all would naturally go through this falling off process. So a senescent cell is one that's had a lot of damage, can't make copies, and in the context of aging, it's one that's figured out how to resist going through apoptosis.
And so in the context of aging, like there are multiple theories about aging and sort of like these hallmarks of aging. Cellular senescence is thought to be sort of a hallmark of aging. Is that correct?
Yeah, so I think of, there's been lots of different theories of aging over the years. Oxidative stress when I was in naturopathic school in the 90s, that idea of the free radical theory of aging was quite prevalent. That's, really been refuted. That doesn't seem to hold out.
Take your vitamins.
Yeah. But I think of, like, in general, there's two camps that most aging theories fit in. One would be an idea of, it's often thought of programmed aging, but fundamentally that as we get older, the genes that we have just run our bodies differently, and that causes us to experience what we think of as aging. Another big camp is aging as damage accumulation. And the idea is that, what manifests as aging is just the progression and accumulation of damage over time in our cells and tissues that causes them to struggle, and that's why we ultimately struggle. And cellular senescence would be one of the underlying mechanisms that contribute to that. And it fits actually neatly into both camps. It's clearly a type of damage accumulation. And it also looks like some of our genes as we get older make more senescent cells. So, it kind of bridges both camps. And you had mentioned the hallmarks of aging. The hallmarks of aging was a conceptual framework of aging that originally came out in 2013. That proposed that there was 9 cellular mechanisms that drive aging in all organisms. And in 2023, it was updated to include 3 more. So now there's these 12 hallmarks of aging, and cellular senescence was one of the original 9. It's still one of the 12. So it's, in principle, one of the core things that drives aging at a cellular level.
And so why then would a cell become senescent in the first place? What sort of things can lead to this change?
Yeah, so the idea of cellular senescence goes back to researchers in 1961 that coined a term called the Hayflick limit. Hayflick was one of the 2 researchers. And before that, it was assumed that if you had a cell in a nice culture dish, gave it enough food, kept the environment nice, it would just live forever. And what they found then is that cells could divide about 50 times and then hit a hard limit and just stop. They would become senescent and not make new copies of themselves. And so that's now known as replicative senescence. And the idea is that as telomeres on our cells get shorter and shorter, so an idea called telomere attrition, each time a cell is copied, at some point, the telomeres get so short that we might be copying a damaged cell if we replicate that DNA, right? So that idea of replicative senescence goes way back, and you'll still see it in papers as one of the potential causes of cellular senescence. But what they found over time is that all kinds of things that just let's call them stress could cause what would be thought of as premature stress-induced senescence. So a qualitatively different type of senescence than replicative senescence. And so, just think big picture, anything that would cause cellular stress. So that might be, cells not getting enough nutrition, cells, accumulating damage that autophagy couldn't repair, cells being disrupted because the mitochondria are performing poorly, external stresses like radiation, toxins, things like that. Anything that can cause cellular stress would cause enough damage potentially for the cell to become senescence because it's no longer repairable. And that's the key idea, like that no longer repairable for whatever reason. And my guess is a significant contributor of cellular senescence and the accumulation of senescent cells with aging is that premature stress-induced cause. So, And then the third piece, and this is one of the reasons that senescent cells have been so much of interest to the research community, is senescent cells secrete this combination of molecules out into the microenvironment around them. And different, like the senescent cells may be being made in a 20-year-old after, running a marathon or doing some intense exercise, would create almost a different molecular soup that they secrete compared to if I did something similar. I'm 62 for listeners. And that stew is called SASP, senescence-associated secretory phenotype. But it's basically characteristic things that they put into the microenvironment. And what research has now shown is the senescent cells talked about in the context of aging put out a really unique soup that can zombify nearby healthy cells. So you'll sometimes see the analogy of senescent cells as zombie cells. That's partly because of this idea that they don't go through apoptosis. They're resisting dying. And partly because they can secrete things into the environment surrounding them that can take otherwise healthy cells and turn them into senescent cells. And so that's the last piece of the puzzle, why they accumulate with aging, is because once we have a certain amount of them, they just make more and more over time.
It's like a contagious disease almost. I mean, aging is sort of a disease if you think about it. I love the zombie cell terminology. The first time I heard that, I think, was on that Limitless series with Chris Hemsworth on National Geographic. I'm sure it came before that, but it's just such an easy way to describe it to patients of, hey, like these cells have now turned into zombie cells, and we got to go get rid of all the zombie cells. And it just like people, like, it just sort of clicks for them. You say the word senescent, and they're like, I have no clue what you're talking about. But zombie cells works. Everybody saw, The Walking Dead, so.
Yep, or the Brad Pitt movie, maybe.
Right. So you mentioned in that brief description you were giving us in the last answer, you mentioned the word autophagy. I think probably important to take just a second and talk about the difference between autophagy and cellular senescence, because there's obviously a difference, but it is a little bit confusing sometimes and to make sure the listeners are on board with this. So what's the difference between the two?
Yeah, absolutely. I've seen it confused even by really smart people in in the scientific community. So the difference is, and like just stepping back, like a cell gets stressed, it's going to now try to respond to that stress, right? So if stress is manageable, the cell's resilient, it'll upregulate antioxidant defenses, maybe make more glutathione, do things essentially to shrug off that stress, become a tougher, more resilient cell. But if stress is more than it can adapt to, then it will take on some degree of damage. And often what gets damaged inside cells are proteins. They become misfolded, as an example, or organelles, which are things like our mitochondria. And what autophagy is, it's a repair program. It's something that would find and recycle the damaged things inside cell and then put, say, the proteins, like the building blocks of those, back to use to build new, better versions of the organelles that it relies on. Same with mitochondria. If mitochondria network's damaged, it will try to repair that. That's called mitophagy, like the mitochondrial version. So it would almost be like an anti-senescence program, one designed to repair before a cell becomes unrepairable. But senescence means the cells now become unrepairable, so autophagy in a senescent cell would keep that cell viable, even though we wanted it to go through apoptosis, if that makes sense. And the analogy often that we use at Neurohacker would be the idea of a plant, right? So if you had a beautiful, healthy plant, all the leaves are, vibrant green, we want that in our tissues, in our organs, right? We want all our cells to be healthy, doing their part. What can happen if a cell, if a leaf gets so stressed that it's not doing its job anymore, it can't get back there, you'd see it to yellow and eventually fall off the plant. So that would be the idea of a senescent cell, right? It should, essentially wither away, go through apoptosis, which apoptosis, for people not familiar with that term, means the cell basically breaks apart in a really organized way, and then the immune system gobbles up that debris and recycles it in the same way a plant that fell into the soil would be recycled to promote new growth. But what happens in a senescent cell is that it's basically stayed on the plant, and then it's causing more and more yellow leaves to accumulate. And if you were a gardener and saw that on your plant, you would know that if you didn't prune them away, that plant would be in, basically peril, right? It could potentially pass away. And so that's kind of the same idea of senescent cells with aging. We just have this gradual more and more accumulation of the equivalent of yellow leaves. The immune system's not doing its job, pruning them away. And that's where this idea of senolytics came in 2015 as a way, all right, well, let's do something else to get these cells finally to fall off the equivalent of the plant, like removed from our tissues. So anyways,
it's sort of like...
I just wanted to make sure, like, we, covered the autophagy and cellular senescence, but the big picture is autophagy is a stress response that would prevent a cell being senescent. But once a cell is senescent, autophagy is still useful to keep healthy cells healthy, but it's not going to do anything to remove the senescent cells.
So from a clinical perspective, what we're really looking to do is encourage autophagy earlier in the process, so that we can sort of heal the cell by, the cell eating up its own proteins and things within the cell itself. But then at some point, you get sort of past a threshold where it's probably not healable. Maybe instead we want it to go through apoptosis prior to becoming senescent, right? And then if we let things go too far without enough intervention, then the cell that's damaged, it's got the brown leaves, makes its way all the way to senescent, and then now there's not much we can do about it. Is that the general sense?
Yeah, because the backup plan would always be the immune system, right? Like, part of its job is to find stress cells no matter what caused that stress. But one of the things that seems like, we know for sure, the immune system isn't quite as competent as we get older as it would be when we're younger, just as a general principle. That's something called immunosenescence, but that's somewhat, the senescence there just means aging, right? An aged immune system. And then there's this idea that some senescent cells, almost, for people familiar with a cloaking device from the old Star Wars TV show or movies, there's some senescent cells that may have always been invisible to our immune system, and maybe over time there's more and more of those. But for whatever reason, the immune system backup plan doesn't work as well as we get older, and so that's part of the reason the senescent cells would accumulate, right? So, they're already resisting apoptosis, and the backup plan isn't finding them.
Awesome. So, now I think is perfect time to start talking about senolytics, and how we can have some sort of intervention on this entire process. I guess the term senolytic is not super new. It's been around for a while. Is that right? Can you tell us a little bit more about what senolytic even means, and maybe where the whole idea began?
Yeah, so I think before the term senolytic, somewhere around 2010, scientists genetically modified animals in an experiment so that they wouldn't produce senescent cells with aging, and noticed that they aged much better, right? They were more vital, their fur was better, their body composition, activity levels, everything was better. So that, almost jump-started this idea, okay, well, senescent cells we always knew were, problematic, but this is super cool. If, something could be done to prevent their accumulation, this was pretty marvelous in terms of what happened in these animals. So kind of the next stage in the evolution was a group of researchers that some were from Mayo Clinic, some were from Scripps Institute of Aging, thought, okay, well, we know some of the mechanisms that cells use to resist apoptosis. Senescent cells are using those. So let's look and screen for compounds that we know can normalize those mechanisms, basically cause a cell that's resisting apoptosis to finally complete that journey. And what they did is identified a couple things that then when they added to cultures of senescent cells would cause those cells finally to go through apoptosis, to finally be pruned off, so to speak. And they coined the term senolytic to describe compounds of that sort that when we took or administered would cause senescent cells to finally go through apoptosis. So that was 2015. That paper came out. The two they originally identified, one was a plant compound called quercetin, which is a type of polyphenol, and one was an immunomodulator medication called dasatinib. And so right from the get-go, that idea of like the mechanistic, let's figure out these protein networks in cells, that senescent cells have kind of shifted so that they're able to resist apoptosis, and let's see if we can do things to correct those mechanisms. And fundamentally, those are what senolytics are. And since then, so that was 2015, 2017, I believe, piperlongumine, which is an alkaloid from an Ayurvedic plant called piperlongum, a relative of the black pepper plant, was identified. Fisetin in 2018, curcumin and olive leaf polyphenols. Some others have just been slowly found over time that these things also can be senolytic. But it all also originally started as just that mechanistic approach. Let's understand these networks they're exploiting. Let's find things that can correct them.
It sounds a little bit like antibiotics and germs. You're these chemicals that have some effect on a cellular organism of some sort, and then it allows the immune system to then do its job. I'm sure it's not that simple. How do these senolytics work? Do they all work differently, or are they all acting on the same mechanism? What's the general approach?
So there's definitely different mechanisms. So like the dasatinib I mentioned works quite differently than how quercetin would. Quercetin, fisetin, luteolin, some of the powerful plant polyphenols work on what would be nutrient sensing pathways that then feed into what the easiest way I would think about it is a cell at any given point in time is always in a point of deciding, should I stay living? Should I go through apoptosis? And there's like specific proteins that, almost the ratio of those would decide which option, door number one, door number two, goes through. And, so that there's many then different pathways that I think funnel in to that decision point would be the easiest way to think of it. And nutrient sensing pathways are one of them. And so some of the like the polyphenols, like the quercetin and fisetin, act on that nutrient sensing pathway, not exclusively, but that would be one of their ways. Piperlongumine, which I mentioned from piperlongum, works in completely different ways. That works on a specific mechanism that senescent cells utilize to resist apoptosis that healthy cells don't. So it like piperlongumine would be somewhat additive and unique. It's, to my knowledge, the only thing so far that's shown to be senolytic in the way it works. Other things, and these are more the pharmaceutical drugs, will often, instead of working on the pathways or the networks that get to this decision point, they'll try to go right after the decision point in a really powerful way. So because of that, they're also, potentially more detrimental to healthy cells than these natural plant compounds would be.
Okay, so senescent cells bad. We want to get rid of senescent cells. We want to send them through apoptosis. Senolytics send senescent cells through apoptosis. So what I'm hearing is I should go buy a bottle of fisetin and just take like 500 milligrams a day, or something like that.
Yeah. So the
simple, right?
Yeah, well, that could be one way, right? So, but I think the dose matters, right? So something could be a senolytic compound like fisetin, but 500 milligrams might not be enough to do the right signal to those nutrient sensing pathways. So what's usually being used in the ongoing studies, many of which they're all registered in clinicaltrials.gov, which is like the study database of ongoing studies. For fisetin, usually it'd be 20 milligrams a kilogram of body weight. And then, so that for, be more like 1,400 milligrams or so for like, a 160 pound person, somewhere in there. And then they do it in a hit and run dosing. So the idea is really to do something that the cell will sense in a really big way, then let it go through its, internal mechanisms to correct apoptosis. So it's not like, like a hormone or a medication or a supplement that you would take every day. It's more like, I think the pruning makes sense, right? Like you don't prune a plant every day, you just do it periodically. And so the way, something like fisetin would be used in both animal studies and in the human studies is in that what's called hit and run dose. You do a really high amount for a couple days and then take some span of time before you would do another cycle of fisetin. And then the other thing, just for listeners, is fisetin's super cool. It looked Mayo was the ones that did the research and identified fisetin as well. At that point, they screened 10 polyphenols. They already knew quercetin, but they put that in, and they found that fisetin was more powerful than quercetin. But the other super important thing, I think, for listeners to understand is senescent cells is a category. So every senescent cell isn't the same. I already mentioned there's, some that, are because of replicative senescence, like that telomere attrition. There's some that may be stress-induced senescence is how they became a senescent cell. There's some that became senescent because they got zombified by a nearby cell. And while they're all senescent cells, they may not respond identically to the same senolytic compound, if that makes sense.
Yep.
And then even at the beginning of the Mayo Clinic's work, they identified both quercetin and dasatinib, but what they found was quercetin was senolytic in endothelial cells and fibroblasts, but not in adipose tissue, while dasatinib was senolytic in adipose tissue, but not some of the senescent cells where quercetin was useful in. And so that stack, that combination of D and Q is how it's usually referred, has been used quite a lot, but because it was additive, neither on their own was particularly senolytic, but when they were stacked together, the combination was. And fisetin was cool because it was more powerful than quercetin. It was active in, as an example, adipose tissue in that original Mayo. So the idea that I think is important for listeners is that something can be a senolytic, but you have to take enough of it to get that benefit. And something can be senolytic, but that doesn't mean it can prune cells away in all of your tissues and organs. So because of that, at Neurohacker Collective with our Qualia Senolytic, we think it's important to put compounds that have activity in multiple different tissues.
Is there, like, when you say that there's it's affecting metabolism within the cell, are these compounds, are they functioning almost like a fasting mimic? Like, is it mimicking the sensation of fasting for the body? Because we know that fasting increases autophagy and cellular senescence. Is that a safe thing to say?
I think it would be. It's probably, always there's some
simplified.
Degree of simplified. Yeah. But I think like all of the plant compounds, as an example that we use in the Qualia Senolytic product, are also capable of promoting autophagy. Because autophagy also, cells are like if you did something like a fast, right, to promote autophagy. So like say Walter Longo's fasting mimicking diet, which is probably the most studied for what's mechanistically happening in a cell.
Yep.
The cells are sensing basically the change in nutrient status around them, primarily in that, like dropping calories, but dropping protein being a big one following his plan. And then that's affecting the nutrient sensing pathways, things like mTOR, PK, AT, things like that. And then that causes, in a sense, like this would be my story. So again, simplified. This, our different cells are saying, okay, the environment's not looking great. I better be more prepared for a future that may, be deficient in proteins, deficient in calories. So what can I recycle? What can I repair and put to better use? And then autophagy gets upregulated. Those proteins that were damaged, they get recycled because we're not getting the external source of proteins in a sense. And cellular senescence, I think, is somewhat similar when you're using these plant compounds that would produce a really strong signal on nutrient sensing pathways. And there's no research on this, but if you take quercetin as an example and Google it, you'll just see, onions are a great food source. But it concentrates in the parts of onions that we would normally throw away when we have plenty of food, right?
Gotcha.
The outer skin, the frilly things at the bottom, right? That's where there's quercetin in the flesh too, but the highest concentration of polyphenols are always where plants interact with the environment because they're stress response compounds fundamentally. Fisetin, you'll see, fisetin's in strawberries, but you'd have to eat a lot of strawberries to get
and the green part.
Yeah, but fisetin also is in leaves and bark. It's a really yellow polyphenol, so it gives like an underlying yellow color to things. And so my guess is evolutionarily the only time humans would have eaten a lot of things with leaves and tree bark and the things we normally throw out is during starvation time periods, right? When it's called the famine winter, World War II in the Netherlands, where there was a part of the Netherlands that couldn't get food in, and they ate whatever they could, right? Straw, leather, tree bark, and it's not great, but that would again, I think, be the only time where we'd have had a big delta in the amount of these plant compounds that really came in. And so what I think is that in a sense, senolytic plant-based compounds, anyways, are almost triggering evolutionarily conserved things that our cells already know how to do. And similar to autophagy, where they're saying, the environment's not great, let me recycle what I can. That somewhere that big change in fisetin, quercetin, these other plant polyphenols is able to then toggle a cell that might have only, it's deciding to hang out, but it doesn't take a lot of votes in the other direction to swing it towards, I'll go through apoptosis, and then the debris can be put to better use. So
super interesting. I was about to make a comment on how I like the intermittent approach because to me, if I think of, these compounds as sort of fasting mimicking compounds, it makes sense that, evolutionarily we've, evolved having periods of famine, all throughout human history. And so it's natural to try to recreate those periods of famine. But I didn't think about the fact that evolutionarily, maybe we also evolved to utilize these compounds through these periods of famine. And that's how the body sort of evolved to help provide senolytics, or the world to provide senolytics to those cells that needed to go through that process. So that's actually super interesting. Is it possible to take too much of these? Like you mentioned intermittent dosing important, so for that sense, like if I was to get aggressive and say like, I just got to kill all my zombie cells. I'm going on a zombie rampage, and I start hitting fisetin at 1,500 milligrams a day for the next month. Like, what am I going to do to myself? Is there a downside?
Yeah. So I think there's, I want to say it's called the Weaver-Flechtner law, something like that, right? You could find it on Wikipedia, but it's an old law, I think 1860s or so. But the general idea of the Weaver-Flechtner law is that receptors, and they were specifically like our sensory receptors, our ears and our eyes, don't respond to quantities, they respond to proportional change. And so analogy that I'll often give is, if you went to the darkest closet in your home or office and, no lights, you light one candle, you'll notice a big difference, right? But if you went into that same closet, there was already 99 candles lit, you light one more, you may notice next to nothing, right? So that quantity of one candle is irrelevant. It's the change in the light that causes our eyes to respond. And when you think of, receptors on cells, they're fundamentally the ears and eyes on cells. So, what I think what's super cool about the hit and run approach and the intermittent use of senolytics, it's creating a big proportional change over those couple days, where my guess is if you took the same amount of fisetin as an example, since you mentioned that, every day, you're now doing more the equivalent of walking into that closet with 99 candles and thinking that one candle is going to make a difference. Yeah. So I think when we're trying to get cells to change behavior, the principle is kind of the same as when we want our hearing or eyes to pay attention to something. We need to create a big proportional change. But if we hold any signal constant for our hearing or our vision, we know that the brain will start to ignore it. And so that would be my concern if someone said, oh, I want to do the senolytic amount of fisetin every day, that it may actually stop working pretty quickly. The cell would start ignoring it. And I think a big part of the reason it works is because of how the cell is sensing the environment around it. So,
yeah, interesting. I mean, would you probably say the same for something like quercetin? Quercetin is interesting because, I don't see a lot of people taking fisetin just for reasons other than trying to promote or trying to take senolytics and trying to promote apoptosis. But quercetin has other potential benefits that some people are taking for, endothelial health, which is presumably from its senolytic effects, or for other things for that matter. Even people were taking it for COVID for a while. So I guess my question is there a downside to taking like a sub-senolytic dose of these medications? Like, quercetin, for example, is often found at like 200 milligrams a pill, right? Is that enough to create senescence, or is there a problem there?
Yeah, so I think as long as we're doing something that creates that proportional difference, we know if it's in supplements someone's listening is taking, then, adding in substantially more for say 2 days a month is still going to cause that proportional change to register.
Gotcha.
But my guess would be, using quercetin every day, it's not creating that proportional change signal. So it won't be per se senolytic used in that way is how I would think of it. Maybe, but my intuition is that for these plant-based compounds, we want to use them in that hidden runway to get the best benefit.
Interesting. Okay. Great. Well, let's talk a little bit about Qualia. This is the senolytic that you guys are making right now. And just to sort of remind everybody, I said this at the beginning of the podcast, but I have no affiliation with Neurohacker Collective, and this is purely informational from my perspective. Tell us a little bit about the Qualia senolytic and sort of what makes it unique and different.
Yeah. So going back to a couple things I mentioned, right, is the idea that senescent cells are a category that they're not all homogeneous or heterogeneous, right? They're qualitatively different. Senescent cells in one tissue may not be able to be pruned away with something that would be beneficial in another tissue. And so I think what makes Qualia's senolytic different is, one, we're using the amount of fisetin that's being used in the ongoing human studies, that 20 milligrams a kilogram as our average dose, right? It would vary person to person. But then, fisetin, I think, is useful in some senescent cells, but not all. More useful in some tissues than not others, where one of the other senolytic compounds that Mayo identified in that fisetin study was luteolin, and luteolin's another yellow polyphenol, seems to have quite a bit of activity in the brain. It's often used in animal studies more for brain applications. Piperlongamine, there was a recent study that essentially used AI to try to figure out, are there plant compounds that will mimic what dasatinib does, since what it does is so different than these other plant compounds. And the number one thing they identified was piperlongamine, right? So piperlongamine, I'd already mentioned, works in a very unique way, but it also seems like maybe it's somewhat of a mimic for, one of these other, well-used senolytic compounds. And then at one point, I also mentioned olive-leaf polyphenols. Olive-leaf polyphenols were found to be senolytic in chondrocytes. So chondrocytes are our joint cells, one of the, the main reasons that our joints perform poorly as we age. So what we did with Qualia senolytic is we tried to, use compounds in the right amounts, select compounds that had activity in a variety of different tissues, and then find ones that had some mimic effect on things that weren't dietary supplement compounds, right? So that's why you'll see we use some soy isoflavones, some milk thistle seed extract, because they have some of the same mechanisms or corrective mechanisms on apoptosis resistance that you would see in a compound like dasatinib. And then, piperlongumine, when we created the product, we didn't know that it also might have a mimetic effect for that. We included it for other reasons. And then, the last thing is we mimic that, 2-day dosing. I've seen a few other, dietary supplement products targeted at senescent cells. And what's commonly the case is, it'll have maybe 100 milligrams of fisetin and some quercetin, and it says take, daily every day for 30 days. I just don't anticipate that low an amount, and that approach is going to be useful for removing senescent cells.
What sort of research have you guys done on the product itself and its effect on cellular senescence or aging, or have you gone about? I mean, this is the challenge is this is hard to test, right? Like you can't cut up the human and see how young they are inside. Like that's just not realistic. What have you guys done?
Yeah, so I mean, before getting to what we've done, I think it's important just to point out what you said, because that's super important, right? Senescent cells, would usually in a like an animal study, they'll take some kind of a biopsy and look at the cells, and even then, the scientist really needs to know what they're doing, because there's no one marker that would say, oh, this is always a senescent cell, or this is always a non-senescent cell, a healthy cell. So scientists will need to look at a combination of things in these studies. So because of that, there's just there's no blood marker remotely close to saying, like, if this changes in your blood, then senescent cells went up or down. So at Qualia, one of the things that we always do is before we would move a product into being made and sold is we do some kind of a pilot study on it. And a pilot study for listeners means there's no placebo group. We're testing it just to see, like, does it seem like it's doing what we hoped it would do. And what we decided on for the Qualia Senolytic product was to recruit people with joint issues and measure before and after subjective responses to Qualia Senolytic. Mm-hmm. And we decided that because I mentioned dasatinib is one of the original two, right? That's a medication. So dasatinib and fisetin is, the most used to date and most studied, and also the one that has the most human studies registered. Fisetin would be second most. But just like us, the big pharma companies trying to, study senolytics are also struggling to figure out what they would measure. And what I found looking through clinicaltrials.gov is that several of the studies just decided, okay, we'll look at joint tissue. We'll use a questionnaire called WOMAC, which is Western Ontario. I can't remember what the other letters, but it's the most widely used way to assess how joints are performing as we get older. So that's what we did. We did it before and after. We saw over 3 cycles. So cycles 2 days, some intermittent time without taking it, 2 more days, some intermittent time, and then a final 2 days, about a 65% improvement in scores in the WOMAC, and thought, okay, that's pretty profound, right? That's a big, big delta in that. And then we did one other pilot study where we used something called the RAND SF36, which is a general health questionnaire that has 8 subscales, one for energy, one for discomfort, one for how our emotional health is affecting our ability to live our lives, one for physical health. So these different subscales, and thought, okay, well, that'll give us a good general idea, because the SF36 is, again, just widely used in health to see if something would have a benefit for healthy aging. And we saw particularly big changes in the energy subscale and that emotional well-being and how it affects our function. So because of that, we moved it forward to being a product that we've had now for about 2 years. And since then, we did a placebo-controlled study. We, again, recruited people that had joint challenges and used the WOMAC and saw, again, that 65-70% improvement over 3 cycles compared to placebo. That was statistically significant. And we saw as secondary outcomes, we used that energy subscale, that emotional wellness, and we saw those trended towards statistical significance. And what that means, it didn't hit the 0.05, but it was close.
And I imagine your users now are probably communicating with you about their own personal experiences, N-of-1 studies. People are coming up with their own ways to test and see if the product seems like it works for them or not. that true?
Yeah. I'm not as directly tied in to, it would be like social media, customer service that gets a lot of those. So I only see what they pass on to me, which is often the more unusual ones, right, that have grabbed there. But we definitely, have got a lot with people with joint issues saying they've noticed a big difference. We get a lot with people noticing a change in their energies. I'm aware of 5 that have come in where women that have stopped their menses, it's restarted. A few people with, like chronic musculoskeletal things. Like a good friend of mine, what I would think of as more of a rotator cuff issue, where throwing was a challenging motion that normalized for him after a few cycles of Qualia Senolytic. And the key concept, and I think like allergies and the way they're usually thought of is the right way to think of it. Allergies are often thought of as a threshold event, right? That there's something in the environment, someone's sensitive, right? We'll just say pollen. And as long as that's below a certain threshold amount, they won't experience allergies. But once they go over, then that's the problem. And that's how scientists think of senescent cells, that as long as tissues are below, some threshold amount, the organ or tissue will still be performing well. When they get close to that or above it is when that tissue or organ starts to underperform, right, and cause things that you and I might think of as symptoms of dysfunction. And so wear and tear accumulates unevenly in different people because of their genetics, their history. And so because of that, there may be someone that's 30 and already has, because of some stress or some other reason, maybe one, thing that's like their Achilles heel, like one area that senescent cells, even at an early age, may be already creating some kind of a burden for them. Someone else, maybe they're 50, it's below the threshold in every single tissue. They take, senolytic compounds and don't notice anything. They're more investing in being a good gardener than, someone that needs as aggressively to prune away the senescent cells.
Awesome. Very, very interesting. What surprised you about the formula now that it's out there on the market and starting to get some results?
The single biggest thing is I didn't think that many people would be interested in this product. When we made it, I wanted to take it, or, I did some of the other people just because I thought, so I did a lot of the, reading up on this 2019 timeframe. In 2020, we made some up just to try ourselves, me, some of the other team members at Neurohackers. But then I couldn't figure out a way forward to test it. And if we can't test a product, we won't bring it forward, right? We need to feel like there's some, like, I guess my thing is like, I always want to know, does something work? Did it do what it was supposed to do? And since we couldn't test, senescent cells directly, it's like, okay, what can we measure? And, so that slowed it down. But even when that was promising, I thought, oh, there'll be some biohackers that think this is really cool, just like I do, right? That would want to take it. Maybe some functional medicine NDs that are working in the longevity space. And, I, often will petition, our executive team saying like, I think we should make this thing. I think it would be really cool. And some of that's always like, oh, well, is it going to sell? Like, what's the market for? And at the time I'm like, we should just make this because it's a cool thing for us to do, to stay on this edge. I think 10 years from now, people will be talking a lot more about senescent cells and senolytic compounds. Many of the other things, that I see in the longevity space, I think we'll think, oh, we thought these were cool, but, in hindsight, not so much. And so even in that pitch, it was like, I don't think many people will buy it, but I think we should make it. And it sold out in 6 weeks, and it's now our biggest selling product. So I'm still somewhat in disbelief that, how well it's done and how people like your listeners, other listeners for podcasts I've been on, are able to understand why, doing this thing that's more maybe an investment in their future health could be an important thing for them to do.
Yep. Awesome. Well, Dr. Greg, thank you so much for coming on the podcast today. This has been excellent. Where can people learn out more about Qualia Senolytics?
So our website is neurohacker.com. You'll find our studies on the Qualia Senolytic published there under studies. Pull down on the menu. For every product we make, I always write a long blog, and by long I mean long, like it's not a 5-minute read. But for Qualia Senolytic, there's one where I discuss just the big picture of senescent cells, and then each ingredient, why I chose it, why we have the amount we have. So for people that want to learn more, those would be great resources.
All right. Well, thank you so much.
My pleasure. Thanks for having me today, Mike.
Thanks so much for listening to the Wild Health Podcast. If you want more daily health education, be sure to follow us on Instagram, which is filled with health optimization how-tos, grocery shopping lists, guided breathwork posts, myth debunking, and so much more. You can find us at Wild Health MD on Instagram.